Hi guys, I really apologize for turning in my oral presentation late. I actually got it done earlier, but then after I was done recording and instead of uploading it to YouTube, I saved it on my laptop and it was hard for me to locate where the file was saved at. Yeah, so I actually emailed the professor to letting her know the problem that I have encountered. So I had to redo it all over again. Thank God I had my information in handy. So my name is Frederick Collins, and I'll be presenting to you prey and predator interactions on the use of aposematic strategies by prey to increase defense against predators. This topic actually, in a way, coincides with our previous lecture on predation in the previous week, and then the predator prey dynamics. The first question I want to ask is, what is aposematism? Aposematism, by definition, is an anti-predatory strategy that involves chemically defended unpalatable prey developing conspicuous signals to help the predators in learning the association between prey unpalatability and then prey signals. Um, some prey actually are cryptic when they are resting. They do not show any form of possession of a defense mechanism until they are provoked. But when they are provoked, they show something, and that thing in the form of coloration or the in the form of coloration, let me put it that way, and it's called dimatic display. So a dimatic display is conspicuous. There's the display of conspicuous abdomen, hind wings, which are normally hidden, and forewings. And then, folks, once again, sorry, for the purpose of this particular presentation, anytime I make mention of a predator, I'm talking about a bird predator. And when I make mention of a prey, I'm talking about an insect prey. So the authors of the particular articles that I read were asking, how do the predators learn to avoid via insect prey? And they came up with two hypotheses. The first one being aposematic signaling hypothesis, and the second one is a facilitation hypothesis. So for the first one, aposematic signaling hypothesis, the predator learns over time by try and error to avoid the prey at the moment of attack. And then for the facilitation hypothesis, the predator learns to avoid the cryptic form of the prey even before they attack it. So that leads us to slide number 2. So, like I was saying earlier, this is the insect or the prey in a cryptic mode, and then this is the post-attack mode. So you can see the link between the facilitation hypothesis and the aposematic signaling hypothesis. So on this picture here, that is an insect called the mountain katydid, Acripeza reticulata, exhibiting dimorphism. And I actually have a video here that shows that. Let me pull this video a little bit up. So that is it without being provoked, and right after it's been provoked, it shows dimorphism. So let's move this video onto the side. And I have another video. What does dimorphism do for an insect, a naive bird, and then what does it do for a bird or a predator that has had several encounters with the prey? So in this case, I need to enlarge the video a little bit so we can see what is going on here. So this bird has had an encounter with the insect, but it did not attack it or eat it. It did not feed on it because it's a naive bird. It does not know what the insect is showing. Is it going to be harmful if it if it feeds on it or what? It does not really know. But in a situation, this bird here, it's a magpie, has had several encounters with the the prey. So as time goes on, it learns to avoid the dimorphism that or the diametric display that the prey is exhibiting, and still will go ahead and the feed on the prey. As we can see, yep, it has fed on the insect. The question is, does dimorphism always confer protection from a predator? And the answer is absolutely no. So in the presence of a naive predator, dimorphical displays tend to be of greater value to the prey. But unfortunately, in the presence of experienced predators which are sympathetic to the prey, they still get consumed. Sympathetic predators learn to ignore the warning signs after several encounters. And we can even, when we bring this to real life, as we try to develop medications to combat bacteria, over time they also develop a mechanism to nullify the medications that we develop over time, as we see in anti in the antibiotic resistance bacteria. Sorry, that was what I was trying to say. So if your defense mechanism is been nullified by your predator, what do you do next? This brings us to the topic of this particular invasive species called the spotted lanternfly, and it has over time learned to up its game by changing its defense mechanism in the process of feeding on a particular plant that confers even enough protection for it. And the name of that plant is called Ailanthus Altissima. Folks, it's not a Nissan Altima, it's Ailanthus altissima. And this particular plant has precinoids containing a chemical called ailanthone, which is very toxic. But then these insects are able to feed on it, and then that confers a lot of protection to them, and then it prevents predators from feeding on them. This is the insect with its in its form showing aposematism, and then this is it with the wings folded. So over time, or during the life cycle of the spotted lanternfly, in instars 1, 2, and 3, it's young, so it's not feeding enough on the sap of the tree of heaven. But as it grows, it gets bigger, and it gets the chance to feed enough. So when you compare the chemical composition or the amount of allantoin in the developing spotted lanternfly in its young from instars 1 to 3, it is smaller than in its adult form, and we can see there's like a hike over here on the graph that I'm trying to show. So how did researchers try to come up with the plan to know that the tree of heaven is actually conferring protection to the insect from predators? So they made a study where two separate bowls, one of which containing seeds that has been mixed with crushed insect, the insect spotted lanternfly. And as I mentioned earlier, the lanternfly has chemicals in it that is toxic. So the birds actually avoided feeding from the bowl that has seeds containing the chemicals of the insects mixed with it. And another study that they did showed they mixed cotton balls, and then they added how do you call it? They mixed the cotton balls with crushed insects, the insect containing the toxin. And then from the figure that I'm showing here, among the 9 wild-caught ticks, that those are the birds that they use for the study, the median marked by the arrow is significantly larger than 0, indicating that the treatment food with a mixture of crushed spotted lanternflies was eating less than the control food without the admixture of lanternflies. Yeah, folks. So you can add enough defense mechanism to the ones that you already have, and then this particular presentation has brought that fact to bear. That does it for my presentation. As I said earlier, I really do apologize for showing it in late. And then this is my reference page. Thank you for being my audience. My name is Frederick Collins. I appreciate you, and you have a good evening.